Hey everyone, welcome to this explainer. Today, we're totally demystifying the application layer. We're going to take those dry, super technical textbook definitions and flip them into the actual dynamic story of how your devices communicate with the world. I am so pumped to guide you through this because, honestly, once you understand this layer, it completely changes how you look at the tech you use every single day.
Think about it for a second. We're on the internet constantly, right? Every single day, we're firing off emails, streaming videos, browsing, gaming. But have you ever stopped to wonder who the invisible translators are? The ones making all this seamless communication happen behind the scenes? Well, thanks to the layered network model, we can use all these services without needing a degree in computer science to understand how the connection is made. Today, we're going to meet those invisible translators face to face. Here's our roadmap for today's explainer. First, we'll break down the application layer itself. Then, we'll meet the network protocols, dive into transferring files with FTP and TFTP, and finally, we'll wrap up with the absolute magic of DHCP. Let's get into it. All right, part one, the application layer explained. Let's look at the absolute foundation of network communication. So whether you're looking at the classic 7-layer OSI model or the more streamlined TCP/IP model, the application layer sits right at the very top. It's the closest one to you, the user. You can kind of think of it as the ultimate customer service team, stepping in to bridge our human-readable software with those complex machine-readable networks. Its main gig is exchanging data between the programs running on your device, the source, and whatever destination host you're trying to reach out to. But here's the thing. The application layer doesn't do all this heavy lifting alone. In the OSI model, it's supported by the presentation and session layers. The presentation layer handles the really vital prep work. It formats the data at the source so the receiving device can actually understand it. Plus, it compresses data to make transfers zippy and encrypts it to keep things secure. Meanwhile, the session layer does, well, exactly what it sounds like. It creates and maintains the dialogues between the source and destination apps. Together, this trio ensures that when you hit send, your data is perfectly prepped and the connection is rock solid. Moving right along to section 2, it's time to meet the network protocols. You know, your computer actually speaks dozens of different languages depending on the task at hand, and it uses different doors or ports to do it. Imagine an IP address as a massive apartment building, and the port is the specific apartment number you need to buzz. For instance, DNS uses port 53 to translate human-friendly domains into IP addresses. Email relies on protocols like SMTP, POP, or IMAP. And the absolute heavy hitters of the web, HTTP and HTTPS, well, they use ports 80 and 443 to deliver all the text and images you see every day. Every single one of these protocols plays a highly specific, totally irreplaceable role in your digital life. All right, section 3. Let's talk about transferring files, specifically focusing on FTP and TFTP. To really appreciate how this works, we kind of need to step back in time. Transferring files between hosts is a massive, fundamental function of IP networks. Nowadays, we do this so easily through web pages or cloud storage. But back in the early internet days, before the World Wide Web was even a thing, everything was purely command line. You couldn't just drag and drop a file. You needed robust, highly specialized text commands. And the real heavyweights of that era, which, by the way, are still incredibly relevant today, are FTP and its lightweight cousin, TFTP. So let's start with FTP. It uses a pretty standard client and server architecture. But what makes FTP so brilliant is that it realizes not all files are created equal. It actually shifts into different transfer modes depending on the file type. On one hand, you've got ASCII mode. This is your go-to for text files. Think TXT, log, or CFG formats. When it transfers in ASCII, it actually converts the text encoding to boost efficiency. Pretty cool, right? Then, on the other hand, we have binary mode. This one is absolutely essential for non-text files. We're talking executable programs, bin files, or images like PNGs. Binary mode sends that raw, unadulterated format to make sure those complex files arrive perfectly intact with zero corruption. Now check out the contrast between active and passive connection modes. In active mode, the client knocks on port 21, but then the server actually initiates the data connection back to the client. It's kind of like leaving your phone number for a business to call you back. But in passive mode, it flips. The client asks for a connection, and the server says, okay, here's a specific port to connect to. That's like a business handing you a direct extension so you can call them yourself. This distinction, it's a total lifesaver when you're trying to bypass really complex firewalls. Okay, so if FTP is your heavy-duty, ultra-reliable option. TFTP, which stands for Trivial File Transfer Protocol, is the stripped-down, lightweight alternative. It operates totally differently. Instead of those complex TCP handshakes, it uses simple, connectionless UDP on port 69. And I mean, it is really stripped down. There's absolutely zero authentication required. You can't even view the file directory on the server. You just blindly request a file to download or push one to upload. It is custom built for raw simplicity and speed, for those times when you just don't need heavy security or complex file management. And that brings us to Section 4, the absolute magic of DHCP and dynamic addressing. To truly grasp the magic here, you have to understand the absolute nightmare that IT admins dealt with before it: IPv4 static addressing. Picture this: an administrator had to manually allocate and physically type in the IP address, the subnet mask, and the default gateway on every single machine. And because humans make typos, if two people accidentally typed in the exact same IP address, boom, IP conflict. Neither could get online. It was just this endless, super tedious game of whack-a-mole. And beyond the crazy manual labor, this setup had terrible flexibility. On an enterprise network, assigning a fixed IP to every single user means awful utilization. A computer might be offline or the user's on vacation for a week, but that IP address is locked up and completely useless to anyone else. Plus, think about modern wireless networks. If you took your laptop from one end of the office to another, crossing into a new Wi-Fi zone, your static IP would break the connection. You'd literally have to do a manual reconfiguration just to get back online in the new spot. What a headache. Enter our plug-and-play hero, DHCP, or the Dynamic Host Configuration Protocol. DHCP was created specifically to crush every single one of those static IP disadvantages. Using a client-server architecture, your device just automatically shouts out a request, and the DHCP server dynamically hands a suitable available IP address right back to it. No manual typing, no human errors, and absolutely zero wasted addresses. It is literally the ultimate enabler for plug-and-play network access. So, I'll leave you with this crucial thought. The next time you walk into a coffee shop, effortlessly join the Wi-Fi and immediately start streaming a video, ask yourself, which invisible protocols are firing off behind the scenes at that exact millisecond to make that magic happen? There's a whole unseen world working just for you. Thanks for joining me for this explainer, and we'll catch you next time.